In this video, we're briefly going to talk about lead compensation, which is the second of our two methods to improve our transient response with cascade compensation. So of course, the other one being the one we just reviewed, which is our PD controller or PD compensation. So unlike our PD compensation, our lead compensation is going to be implemented using a passive network, so resistors, capacitors, inductors. And so what that means is that ultimately it's going to be cheaper. However, as we're going to see, we also are going to have to introduce a pole along with our desired zero. So we're going to need a new pole along with our desired zero. However, one thing to keep in mind that we've mentioned previously is that this lead compensation does reduce the noise from differentiation compared to an ideal PD controller. So it reduces noise from our differentiation. Okay, so let's just consider some general system where we want to change the root locus to go through some desired pole, and of course that desired pole isn't on the original root locus, so we can't just adjust our gain and get to that point. So I've drawn sort of generally here our desired pole, and let's say these green lines represent our magnitude and angular contributions from these open loop poles and this open loop zero. So what I'm saying above is that we need to introduce not only a zero, but also a pole to help perform this lead compensation. And so let me sort of arbitrarily put a zero for our compensation and a pole for our compensation over here. So our pole should of course be an X. So let's say this is Z sub C, this is P sub C, so pole for compensation, zero for compensation. And let me draw a line from each of those to our point of interest. So we have something that looks like this. And so let me come back and label, so let's use green, let's label these guys as well. So let's say this was our 0, 1, this is our P1, this is our P2. And so the green is our original system, and the orange is our compensation to that system. So now we can talk about angular contributions from each of these. So if I go left from right, I can say that this angle here is going to be theta 1, this angle is going to be theta 2, and let me switch over to green. So this angle is going to be theta 3, theta 4, and theta 5. Now, of course, this is for some specific system with only two open loop poles and one open loop zero, but the same idea can be generalized if we're talking about more or fewer of those open loop poles and zeros. Okay, so what we know is that for a closed loop pole to be on the root locus, we have to have certain conditions being met. So we're going to go back to particularly that angular contribution that we looked at when we were talking about our PD controller. So for a closed loop pole to be on the root locus, we know that we have to have the sum of our zero angles minus the sum of our pole angles equal an odd multiple of 180. So in this case, we have two zero angles. It's going to be theta 2 plus theta 5 minus the sum of our pole angles, which in this case we have 3. We have theta 1 from our compensating pole plus theta, theta 3 and plus theta 4 for our original poles. And so we know that that has to be some odd multiple of 180. So 2m plus 1 times 180 degrees, where again, m is just going to be 0, 1, 2, so on and so forth. So just any integer value. So the overall angular contribution from our compensation network is just going to be theta c, which is equal to theta 2 minus theta 1. So theta sub c, which is equal to theta 2 minus theta 1, is our angular contribution from the compensation network. So angular contribution from compensation. And so we can recognize that one of two ways. We can see clearly, from up here in our previous equation, theta 2 minus theta 1 are the two terms that are related to our compensation network. We can also realize that graphically, if we sort of draw a line parallel to the real axis up here. So using trig, or rather geometry, we know that this angle here is going to be theta 1, and this angle between here and here, our ZC line, is going to be theta 2. So then the difference between these two lines is going to be theta sub c. So that theta sub c is going to be sort of the angle that we're trying to match to a desired compensation term. And so what that means then is that if theta c is really the important factor because that's what's adjusting our system, then we actually have infinite possibilities for our PC and ZC. So we have infinite possibilities or infinite possible solutions for a desired theta c by moving our PC and ZC. So basically what that's saying is we can move these two lines around, and as long as we're moving sort of both of these endpoints such that this angle theta c is preserved, then that's going to be an acceptable solution. Now, of course, moving those around is going to change other parts of our system. So for example, if we have some theta c, so for a constant theta c, but if we are varying or changing, choosing different values of our PC and our ZC, so items that will change or vary as we're moving, again, we're moving PC and ZC, but we're keeping our theta c constant, we still can see change in various things. So we can see change in our static error constants. And so ultimately that means changes in our steady state error. We can also see changes in the gain required to reach a certain point. So that also comes into play with our steady state error as well as other items. We might also be making it either appropriate or inappropriate to use our second order approximation and therefore our second order equations if we're talking about time response. And of course, ultimately, all of these things are affecting our transient response as well. And so we're not going to go through a detailed example due to limited time. However, I would encourage you to look on page, let's see, I only have the 7th edition page number. I did not update that. So page 471 in the 7th edition should be relatively close to some of the 8th edition page numbers I mentioned in the previous video. But the example number is going to be the same of 9.4. And so from that example, what we can see is our general approach is going to be to choose one of the two. So either our pole or our zero location. So general approach is to choose ZC or PC, and then we get the second, so we get the other from the required angular contribution. So from our required theta c. Now, of course, which one we choose and what value we choose for our zero or our pole. So it's somewhat arbitrary, but we should also be basing that on an educated guess based on how it's going to affect some of these parameters above. And then again, once we choose that, we know what our angular contribution is going to be from either our theta 1 or our theta 2. So we can determine what our other either pole or zero needs to be in order to keep this required overall angular contribution from our compensation network.